In this video, we will practice with geometric series and we will see something called the divergence test. So we now have the official theorem. A geometric series with common ratio r converges if the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than or equal to 1. When it converges, i.e. when the absolute value of r is less than 1, then we can say the actual sum can be computed as c divided by the quantity of 1 minus r. So, first example, does this series converge or diverge? If it converges, what's the sum? As we saw in a previous video, this is a geometric series that can be written in the form the sum as n goes from 0 to infinity of 1/2 times the quantity 1/2 to the nth power. This is a geometric series where c is this 1/2 and r is this 1/2. So since r is 1/2 and the absolute value of a half is less than 1, we are under the condition where this series will converge. And since it converges, we can then say that the sum will be of this form. That is, this is equal to 1/2, which is the c value, over 1 minus 1/2, which is the r value. And of course, the denominator here is a half divided by half equals 1. And if you recall, we looked at this geometric series numerically to start in the previous video, and it appeared to converge to 1. And we now are certain that the sum is exactly 1 since we've done it analytically. Let's now look at a couple more convenient properties and continue to work with our geometric series. If you have two series of convergent infinite series, C can be any constant, then the following are true. The sum of the constant multiple of the ANs is the same thing as if you pulled the constant multiple out front of the sum. And the sum of the ANs and the BNs is the same thing as if you took the sum, or the difference that is, of the two series separately. So what we want to now do is potentially use one or both of these to show that this particular series here is a convergent series. We'll also find its sum. Let's use this property here to show that this one converges. So while we have a sum of the difference of these two expressions, we know that if they converge individually, then the sum will converge to the sum of each of those. So let's look at the sum as n goes from 1 to infinity of 3 over 4 to the n power. And let's subtract from that the sum as n goes from 1 to infinity of 2 over the 5 to the n minus 1 power. If each of these is a convergent series, then their difference will be the value of this series. Well, we got to show that these are in fact geometric series. In order to be a geometric series, these need to have a common ratio r. So let's first rewrite these. Of course, this one is the sum as n goes from 1 to infinity of 3 times 1 over 4 to the n. We're trying to get a specific number raised to the power of n, not just the denominator of 4 raised to the power of n. The reason this 3 was brought over here was because of the next move. We can rewrite this as the sum as n goes from 1 to infinity of 3 times 1 to the n power over 4 to the n power, because 1 to the n power for finite values of n is the same thing as 1. So notice I couldn't just raise the 3 to the n power, because 3 to the n power in general is not equivalent to 3. Now this series can be rewritten as the sum as n goes from 1 to infinity of 3 times 1/4 to the nth power using laws of exponents from basic algebra. Even though our series here is starting at 1, once we've gotten a number raised to the nth power, we can see this is officially a geometric series. And the actual r value, or the common ratio, is this 1/4. However, this is not the value of c since this is starting at 1 instead of 0. We will compute the value of c in a little bit, but we now know this is a geometric series with a common ratio of 1/4. We can do the same thing with this series here. We've got minus the sum as n goes from 1 to infinity of 2 times 1 over 5 to the n minus 1th power. Now, raising 1 to the n minus 1 power would be the same thing as 1 for all finite n, so we can rewrite this as the sum as n goes from 1 to infinity of 2 times 1 to the n minus 1 over 5 to the n minus 1. And using our exponent laws from basic algebra, we've got the sum as n goes from 1 to infinity of 2 times 1/5 raised to the n minus 1 power. And now, even though this is n minus 1, this is still the ratio, or the common ratio, 1/5, because technically using the exponent laws, you could take out a 1/5 to the minus 1 power, and we'd have 1/5 to the nth power still. So this is a geometric series as well, with a common ratio of 1/5. So since the common ratio of this one is 1/4, which has an absolute value less than 1, and since this geometric series has a common ratio of 1/5, which has an absolute value less than 1, we know that each of these series converges. So that means the difference together is also going to converge. And it will converge to the difference of these two sums. Let's find these two sums. So this is equal to, now the sum formula is C over 1 minus R. C is not this value 3 for this series, and it's also not this 2 for this series. That is because in order for C to be the value that R to the n is being multiplied by, you need a lower bound of n equals 0, and here we have a lower bound of n equals 1. We also have that lower bound of n equals 1 here instead of n equals 0, and we also don't already have it written as to the nth power. We have it to the n minus 1 power. So you can rewrite each of these to specifically be in this form, or you can just recall that C itself is the very first term in the series. So since we start at 1 here, the first term of this series would be 3 over 4 to the 1, which would be 3/4. And the first term of this series would be, when n is 1, is 5 to the 1 minus 1, which would give you 1, and 2 divided by 1 is 2. So the C value for this series is 3/4, and the C value for this series is 2. And using our formula, we now have C, which is 3/4 for the first series here, over 1 minus, we found that R was 1/4 for the first series. Now minus, we've got the sum of this series is the C value, which we said was 2, over 1 minus the R value for this one was 1/5. And now we can do the computations here and find out what the sum is of this convergent series. So here we've got 3/4 over 3/4 is in fact just 1. And here we've got 2 over 4/5. 2 over 4/5 is the same thing as 5/2. And 1 minus 5/2 is equal to negative 3/2. We have shown that this series converges and that it specifically converges to, or has a sum of, negative 3/2. Now that we've done some practice with geometric series, let's look at some additional convergence or divergence tests, because not all series are geometric. So here is a simple theorem that can sometimes be used to show a series diverges. And the divergence test says that if the sequence of ANs does not converge to 0, again, it does not converge to 0, then the series of the ANs diverges. So let's try an example with this. Use the divergence test to show that the sum as n goes from 1 up to infinity of 2n minus 1s diverges. In this case, our a sub n's are the 2n minus 1s, and we want to see if the sequence of an's does not converge to 0. That means we need to take the limit as n approaches infinity of our a sub n's. Now, this is a simple linear function with positive slope, so that means this limit as n approaches infinity is going to take off to infinity. Up here at the divergence test, they said if the sequence of a sub n does not converge to 0, and notice this limit is not equal to 0, that means that we can conclude that the series itself diverges. So our final conclusion here is that the series as n goes from 1 to infinity of 2n minus 1 diverges. It's a pretty simple test to use, but let's make sure it's clear what this means. So why does the divergence test make sense? Here's a graph of the sequence above to help you explain it. So of course, a sub n equals 2n minus 1 is just the series of dots along the continuous function y equals 2x minus 1. Now, it's pretty clear why this thing diverges, because we are taking the sum of all these values. In other words, we are adding up the lengths of these vertical lines. And notice if we were to continue to go, these vertical lines, their length gets even longer. And if we've got infinitely many of them, then their lengths will add off to infinity. Now that we have a theorem for geometric series, and we also have what is called the divergence test, let's look at several problems together where it doesn't tell you what to do, and we have to decide which test to use. Do the following series converge or diverge? If they converge, to what do they converge? So as of now, we've got three series here, and we only have the divergence test, or we know when a geometric series converges or diverges. So when you first look at these three, it does not appear that this one would be a geometric series because these are linear functions. There's no exponential expression in here. Whereas in here, we look like we've got some sort of exponential expressions. So each of these, I'm thinking these are perhaps geometric series. This one is not. So the only thing else we have is to use the divergence test. So the divergence test requires us to take the limit as j approaches infinity of j plus 1 over 2j minus 3. Now, if we thought about the continuous version of this, x plus 1 over 2x minus 3, that's simply a rational function, and it has the same degree. The numerator and the top both have the degree of 1, so the limit would be the ratio of the leading coefficients. So that would be the same here for this sequence, meaning this limit is 1/2. Now, by the divergence test, since that limit is not equal to 0, can conclude that the series as j goes from 1 to infinity of j plus 1 over the quantity 2j minus 3 diverges. Now again, these two look like they are potentially geometric series. We need to rewrite them to see them in their geometric form. So first, we cannot pretend like this one is not here. We need to deal with that. Well, of course, using our distributive property, we can rewrite this as the sum as n goes from 1 to infinity of 1 by 3 over n plus 2 to the n over 3 to the n. We can also write each of these as exponential expressions. Since 1 is the same thing as 1 to the n for finite n, this can be rewritten as the sum as n goes from 1 to infinity of 1/3 to the n power plus 2/3 to the n power. And since these individually would be geometric series that have a common ratio of absolute value less than 1, then we know that each of those individually would converge, meaning we can split this up. So we have the sum as n goes from 1 to infinity of 1/3 that quantity to the nth power plus the sum as n goes from 1 to infinity of 2/3 to the nth power. And since those each converge, we can find their sum. We've got this is equal to, remember the sum formula is c over 1 minus r. These are our r values, our common ratio. However, c is not 1 because the lower bound here is 0. So c again just represents the first term of the sum. So whatever your first n is, plug that in, and whatever term you get, that is your value of c. So let's go ahead and do this. We're going to get c over 1 minus r for this series. So c, when n is 1, you get 1/3 to the 1 power. So c is specifically 1/3. And then that should be over 1 minus r, and in this case, r is this growth factor of 1/3. Then we also have plus c over 1 minus r for this series. So for this series, when n is 1, you get 2/3 to the 1 power is 2/3. That is the very first term. That means that's c. So you get 2/3 over, and then 1 minus r. This actual 2/3 right here, that common ratio is our value of r. Plug that in for r in our formula here. This is now equal to 1/3 by 2/3 plus 2/3 by 1/3. And 1/3 divided by 2/3 is a half, plus 2/3 divided by 1/3 is 2. Hence, this series converges, and it converges to 5/2. Let's now pursue this last example here. Let's first rewrite this as the sum as k goes from 1 to infinity of 1 over 2 to the k plus 3 to the k over 2 to the k. And of course, since 1 to the k is equal to 1, For finite values of k, we can rewrite this as the sum as k goes from 1 to infinity of 1 to the k over 2 to the k plus 3 to the k over 2 to the k. And then using our laws of exponents, we can write each of these as the sum as k goes from 1 to infinity of a half to the k power and plus 3 halves to the k power. But now you may notice that if we were to split these two things up here, this would be a divergent geometric series. So since this one here would diverge, even though this one would converge, the sum of those, because this one will diverge, this whole sum will also diverge. So we are going to simply state that this is a divergent series. Please recall the only time that you can use the formula C over 1 minus R for the sum is when you have a convergent geometric series. Since this is a divergent geometric series, while you could technically do the computation of C over 1 minus R, that is not what this sum is equal to. This sum is not finite. This sum diverges.